Yes. Sanidhi, am I audible?
Yes, ma'am.
All right. So yeah, Sanidhi, one numerical I told you that we'll be discussing based on the conservation of center of mass. Let's discuss that.
Okay, ma'am.
See, this is a question from your NCRT. Let me just explain you and see, look at the figures. The question part I'll explain. A man is standing on a wooden plank. Okay. And when the person is standing on the plank is basically a wooden piece, a log of wood, which is present on the river side. And near the bank, it is just adjacent to the wooden log. Now see, the person is standing on the corner, means the periphery of it. Okay. Now see, what happens is it says that a man of mass M, means small m, stands on a wooden plank of mass capital M, floating on a river near its bank. Now the man starts walking. So what happens when he's at the periphery? This way he is balanced. Now you imagine, have you ever sat on a boat?
Yes, ma'am.
So when you actually jump on the boat to load yourself, the boat moves. It's not on a stable surface because it's on water. It's floating, and the rest of the things you have already, no, you have not already studied. You will study in fluid mechanics, buoyancy and all. So the boat moves. This you must have experienced, an unstableness, unsteadiness that is present over there. So when the person is standing on the periphery of the plank and there's a gap, he is at a distance of length L, means he is completely at one edge of the plank like this. Now he begins to move forward. But as a result of which, what happens? Technically, what he wanted to do was he wanted to just get off towards the other side of the bank so as to reach the safer side. So he could just walk up here and reach up here. But the problem is that the surface is not stable. So when the person will walk on the plank will also be shifting backwards. And eventually it results in this kind of situation where the person is there at the periphery of the plank, but the plank has also shifted by some distance from the bank of the river. Have you got this point? This happens even when you step up on a boat. What will happen? Boat tends to move away from where you have to land. It never is adjacent to your flat, safe surface, right?
Yes. Yes.
So, let's just understand the masses and everything and the whole concept over here. The person is here on the periphery, and this is the edge where the person is present. So M mass is there, and capital, let's say small m is the mass of the man and capital M is the mass of the wooden plank. Now the person is at a distance of length L, means from the periphery the person is separated by this distance of length L. So see what we are going to do here. Remember, whenever external force is not acting in your system, whenever you don't have any external force acting in your system, so as a result of which your body, see, whatever is the center of mass of the system. Yesterday, I discussed a point with you about the system and internal forces. Yes, this one. Remember that internal force can never affect the center of mass, while the external force definitely affects the center of the mass. So here, when we talk about the center of masses, look, in the both of the cases, case 1 and case 2, the center of mass will be conserved because there is no external force acting in your system, and only the external forces can disturb your center of mass. Your center of mass won't be disturbed like this. So this is a wooden block, and the person is here. So what we are going to do, we are individually going to write down the center of mass. One more thing, when I'm saying the system, the mass, not mass, let's say the man plus Planck, this is the system. Man plus Planck is the system. Now let's write down everything in detail about each and every point. So the man is there on the periphery. Okay. M1, let's say 1 is for man. Mass of the man will be M. And the position for the center of mass, see, we always have to choose a reference axis. This I have told you multiple times. Whenever you have the questions from the rotational chapter, you'll have to focus on the periphery. So, see, you have to choose an origin or an axis. See, for the rotational part, you'll have to focus on the axis. And when you are talking about the center of masses, you'll have to focus on the origin. Because I discussed with you that the center of mass is actually not away from the origin. Right? This is not away from the means center of mass is not in your rotational motion. I made you write a point. It's valid for translational motion. Remember?
Yes.
We have moment of inertia. So in moment of inertia, we'll be using an axis, and here also we'll be using an origin. So everything will be with respect to the origin. So Sanidhi, can you tell me from the figure what is the value of x1? Yeah, Sanidhi. For the man, what's the separation from the origin? Look at the figure.
Mom, the case number 1, right?
It's just the case number 1. See, any distance you can see from the origin. This is my reference axis origin.
From the origin, it will be L by 2.
Yes, correct. L, not L by 2. Where is the person standing? Here at the edge.
Okay.
And this complete separation is L, right? So this will be L. Now let's say M2, this is the Planck. Its mass is capital M. X2. Now see, where is the center of mass? See, I discussed with you whenever you have a rod of length L, we can replace the entire rod with a single point mass. That is our center of mass, correct? So for the center of mass, this is the center of mass placed, okay, in the center point of the wooden plank. That's why you should know, as we derived also, that L by 2 should be the point of the center of the mass, okay? So here, this center of mass, just instead of considering the whole plank, just take the center of mass. Now tell me, Sanidhi, where is the center of mass situated from the origin?
Mom, L.
L by 2, center
by
of
2.
mass of the plank is this. Okay, this is L by 2 and the complete separation is L. So this is L by 2. This is the first one. Let's talk about the second scenario. Or no, before that, let me write down the formula. See, as we discussed, the center of mass will be M1 into M1 x1 plus M2 x2 divided by M1 plus M2. So M into L plus capital M into L by 2 divided by M plus small m. Right? Now the person has shifted forward and the plank has shifted backward with a little distance x. Now this x distance is not given. This is a distance that I have assumed. Okay, this distance is not given. This is a distance that I have assumed. So here in the second case, let's write down few things first. M1 will still be, the mass will never change, mass will still be this. Can you see from the figure, Sanidhi, an answer by how much distance is the person situated? By? X, correct, absolutely right. From the river's bank, it is situated at a distance of x. Now, this is the value of x that you have to find out. That's the task of this question, okay? How much the plank has shifted backwards. M2 will be, mass of the plank is capital M, and the distance will be Now see, Planck's center of mass is here. Now where is the Planck? What is the distance of this to the origin now? Can you tell?
Mom, the distance?
For x2? This is now, see, earlier we chose the central point that were where the center of mass was located. From this point we saw, right? From this point we saw the separation. Now if the Planck moves here, so where is the point now? Point is here. What is the separation from the origin? What is the displacement?
X plus L.
What?
Mom, the displacement will be X plus L2.
X plus L by 2. This
By
is X. This is L by 2. So total will be X plus L by 2. So X will be M into X plus M into X plus L by 2 divided by M plus small m. Okay. Now the center of mass will be conserved. So there will be conservation of the center of mass. That is F external will be 0. Because F external is 0, so center of mass will be conserved. I can basically equate these two equations. M into L plus ML by 2 by capital M plus small m equal to, this is mx plus mx plus capital ML by 2 divided by m plus small m. So look, capital M plus small m, capital M plus small m. This gets cancelled. So we are left with ML plus ML by 2 is equal to mx plus capital MX plus ML by 2. See, this ML by 2 will be cancelled. So from here, ML, this is equal to X, that is M plus capital M, small m plus capital M. So X we had to calculate, that will be ML by small m plus capital M. Got it, Sanidhi?
yeah, Mom.
All right. Please write this question properly in detail every point. It is very important because it sometimes becomes confusing. First, note down the question, then the solution.
Mom, how many marks may this question come from?
Five. This can come for 5 also. Okay. But usually these kinds of questions, usually they come for 3 marks. But it can come for 5 marks also, maximum. But 3 marker. It's a 3 marker question.
Okay. None. Done, mom. Done, mom. Done, ma'am.
All right. So this momentum part, could you write it yesterday?
Yes, ma'am. I did.
Oh. So just a very small, easy question. I think this is in the NCERT example. So if the child jumps off the car towards the right with a velocity of v with respect to the ground. The person is jumping off the car towards right with a velocity of u with respect to the ground. Find the velocity of the car after the jump. Means if this goes here, so as a result, the car will be going here. Let's say some velocity v. Momentum conservation of momentum, center of mass. Okay, that's what we discussed in the last class. That conservation of momentum of center of mass. Center of mass here of this man and this one, the car, their center of their momentums, their center of masses, momentum will be conserved, not position, not velocity. So momentum of the child, let's say, his center of mass will be equal to momentum of the car. So I just write it as car and this as child. Okay, so this is equal to m into u for this, and this is equal to m into v. Okay, the signs are opposite. You can take one as positive, one as negative also, but right now I'm just focusing on the magnitude because it says velocity of the car when it jumps off. So v will be equal to mu divided by m. That's it. Fine, momentum is conserved. Center of mass is velocity you had to calculate. So you've calculated it as mu and all. Got it, Sanidhi?
Yeah, ma'am.
Right, this also now we'll move towards the kinematics of circular motion.
Done, mom.
Okay, see, Sanidhi, not questions, few equations we've already studied when we had the second chapter, motion in a straight line. So three equations were there. Remember that linear displacement becomes your angular displacement. Now, what is angular displacement? What is angular velocity? What is angular acceleration? All these things we have already studied in the laws of motion. Remember, I told you that a portion we are already doing in laws of motion so that this eases our work in the rotational chapter, right?
Yes.
So, theta, what is theta? What is omega? What is alpha? This you have to refer to your laws of motions, circular motion portion that we have completed. And rest of it, if needed any help, if you want me to repeat any part, please let me know, but revise it from there. That part I'm not doing because we've already done in depth. Coming to the equation straight away and the analog. See, your linear displacement will become angular displacement. Initial velocity will become initial angular velocity. Initial final velocity will become final angular velocity. So just to distinguish between the angular velocities, initial and the final value, we put a not in the initial because u and v are there for the linear, but for the angular we don't have any other symbol. So omega is only used for angular velocities. So a not in the subscript is put so as to distinguish this between angular velocity, initial and the final value. And the acceleration is alpha, that is the angular acceleration present. So three equations we have. First is, tell me the equation, Sanidhi. Equations of uniformly accelerated motion. Second chapter. What all equations were there?
Mom, equation.
Uniformly accelerated equations. S, U, V, A, T. Connected all of these.
S is equal to UT plus half AT square.
Correct.
Then B square is equal to U square plus 2AS.
Correct. V square minus US. 2S. Correct. One more. First one.
V is equal to U plus AT.
Correct. V is equal to U plus. Right. So see, when we put in their analogs, same equations we are going to write in terms of their analogs. So V is the final velocity. Omega is equal to omega naught plus alpha t. This is the equation. We'll derive it, though I'll make the derivations right now so that you can see also. But same equations are there. Similarly, theta is equal to omega naught t plus half alpha t square. Third, omega square minus omega naught square is equal to 2 alpha theta. So I'll suggest just remember this, their analogs, and the analogs are not difficult to remember. Linear displacement will definitely become angular displacement. The initial velocity and the final velocity will turn into angular velocity. Linear velocity into angular, for initial just put it not in the subscript. And acceleration becomes angular acceleration. So this is not difficult to remember. These three equations you already know. So you just have to convert the analogs, and these equations are not difficult for you, right? Is it, Sanidhi? Okay, then copy down this page. Then if time is there, we'll discuss the derivations of each.
Okay. Done, ma'am.
All right. See, derivations are very simple in this. We'll just have to perform a simple integration for all of these. So when we start with the equation of angular velocity, we know alpha is equal to d omega over dt. So from here, this we have already done. That's why I'm just writing it. So from here, if I wish, I can say d omega is equal to alpha dt. Okay, and we integrate it from some initial value. Let's say this initial velocity will be omega naught, final will be omega. That's how we integrate. We put the limits according to the variable that is present. And this is from 0 to t. Now, omega from 0 to omega is equal to alpha is a constant, it will come out. And then we'll be left with integral of dt from 0 to t. So this will be upper minus lower limit. That will be omega minus 0 is equal to alpha t minus 0. Means here also same thing. I'll just rewrite one more step. That is t from 0 to t. I hope you remember integral of dt is t. Sanidhi.
Yes.
So this will be omega. I have written 0 over. This is omega. So omega minus omega naught is equal to alpha t minus 0. So omega is minus omega naught is equal to alpha t. Omega is equal to omega naught plus alpha t. That's the first equation of motion. Fine?
Yes, ma'am.
Okay. Now see, second equation of motion, theta is equal to omega naught t plus half alpha t square and all. See, omega is equal to d theta over dt. This also we have done. Angular speed is rate of change of linear displacement. So from here, d theta could be written as omega dt. Okay. So integrating, when we integrate it, let's say from some initial value 0 to final theta, and this is time, so 0 to t. Now what we do, equation of omega, from the first one we'll put omega naught plus alpha t. Here we'll put this value in here. So we will get, this will be theta from 0 to theta. Omega can be written as omega naught plus alpha t dt, integrating from 0 to t. So this will be theta minus 0. This is omega naught dt, integrating from 0 to t, plus alpha t dt from 0 to t. So this is theta. This is omega naught t minus 0, plus this is alpha. This will be t square by 2 from 0 to t. In fact, here also I've skipped one step. This will be t from 0 to t. So see, theta is equal to omega naught t minus 0 plus alpha by 2 t square minus 0 square. Theta is equal to omega naught t plus half alpha t square. Got it, Nidhi?
Yes, ma'am.
All right. Last one we have omega square minus omega naught square. This we'll do later. First, you copy it down from here. Okay.
Okay. Done, mom. Done, mom.
Yes, okay, Sanidhi. So I'll complete this on Saturday now. Okay.
Okay, mom.
All right. Okay then. Thank you.
Thank you, mom.